Welcome to Spring LIB.
Okay, we have a few carbocations, which I will sketch briefly. Okay, so we've got a carbocation here, and 1, here, and 2, here, and 3, here, and 4, and 5, and here, and 4. Now remember, when we're not dealing with any double bonds or any other functional groups, the primary concern for stability of a carbocation is the degree of the carbon on which it sits, right? That is the carbon primary, secondary, or tertiary, which is to say, does it have 1 bond to carbon, 2 bonds to carbon, 3 bonds to carbon, right? So 2 bonds to carbon right here, right? 1, 2. This is secondary. 2 bonds to carbon here. This is secondary. 2 bonds to carbon here. This is secondary. 1 bond to carbon here. This is primary. Versus 1, 2, 3 bonds to carbon on the carbon that bears the carbocation here. So number 4, the tertiary carbocation is going to be the most stable. And coincidentally, 5 would be the least stable. So you're really just counting the number of carbons, bonds to carbon that the carbon which bears the carbocation has, and selecting the one that has the most bonds to carbon. That is the most stable. As for the second question, this is a question about oxymercuration-demercuration, reduction of an alkene. Okay, recall that oxymercuration-demercuration is Markovnikov addition of an alcohol, an OH group, but unlike Markovnikov addition of an OH group with acidic water, this is not going to induce rearrangements because there's never a carbocation intermediate, right? So oxymercuration, demercuration is Markovnikov, no rearrangements, versus acidic water is Markovnikov, but rearrangements can happen. Hydride shifts, methyl shifts, etc. Okay. Which statement is true in the oxymercuration-demercuration-reduction of an alkene? Markovnikov orientation and syn addition occur. Markovnikov orientation and anti-addition occur. Anti-Markovnikov orientation and syn addition occur. Anti-Markovnikov. Okay, so this is about syn and anti-addition. And to this, the important thing is, well, we already know it's Markovnikov. We just said that. Right. And in the mechanism, it's important to recognize what they're getting at here is that we are attaching something to both sides of the double bond. For a moment, one side is going to get a hydrogen. The other side gets like an acetate. Okay. And the addition across that double bond of the intermediate acetate and the intermediate, well, the hydrogen will finally be on there in the final product. Oops. Happen on the same face of the alkene, right? During the actual mechanism, right? So this would be syn addition. So in the step in which the acetate is first added to the double bond before it's converted into the OH, it is added syn to a hydrogen that is also added. So it would be fair to say that oxymercuration reduction of an alkene occurs in Markovnikov orientation and syn addition, which is answer A.